Okay, so welcome everybody. We'll get started here. So let's take a peek at the syllabus really quick and just make sure we're kind of all on the same page about what's happening for the week. So here we go. Okay. So you will, there we are. Wow, we're already sitting, it's crazy. We're already sitting at week 11. So we're making our way through the semester for sure. Cool. We've got chemical reactions this week. Remember, we started that early. So we're already sort of into this chapter. You will have a lab that's due on Sunday. You also have some homework that's due on Sunday, so make sure that you get to that. We are not going to meet on Wednesday. We're just going to call it an election mental health day. So please feel free to catch up on assignments and things like that. I mean, I will be around. So if you have questions, feel free to email me. But we're just going to bypass lecture. Any questions on, oh, and then let's see. So we've got chemical reactions. Then the following week, we'll be doing quantities of chemical reactions. And then our next test, test 3, is going to be 11:15 to 11:16 is when that'll be open. Okay, that test is a little bit more challenging, I would say, than the other tests. So you may want to start reviewing and studying for that now so you don't smush all that right before the test, because it does cover chapter 6, which was all on the moles. It covers chapter 7, which is this equation stuff, and then it'll cover chapter 8, which is stoichiometry. Questions on where we're sitting as far as the semester is concerned? No. Okay, once we get through that third test, we are 3/4 of the way there. So it will happen very quickly, I feel like, after that third test. The semester will just sort of come to an end. Okay, so we left off, we had been talking about precipitate reactions, or the possibility of a precipitate reaction. So we have two things, let's say these two things here. So I have sodium carbonate and copper 2 chloride. And we are going to mix them together. This is aqueous and this is also aqueous. We're going to mix them together and we want to see if a precipitate forms. So I want you to go ahead and find the partner. I'm going to write this on my other. So we had with sodium carbonate, Na, 2CO3, and this was aqueous. And we're adding it to copper 2 chloride, CuCl2, aqueous. So both of these things are aqueous. I want you to write the possible products. And then if you have a textbook near you and you've got those solubility charts, you can actually go ahead and see if either of them are insoluble or precipitate. So flip-flop partners, make some new compounds, balance it, see what the phases are. I'll give you 4 minutes for that. And while you're working on it, if you have questions, throw it in the chat or just turn off your mic and you can just ask me. Okay, so looking at this one, so we're going to flip flop the metal on the first one. Use a different color here. So the metal on the first one is going to go with the non-metal on the second one. Sodium has a +1 charge, chlorine has a -1 charge. So I'm going to combine it as NaCl. And I know that's aqueous because it's table salt. I know it dissolves in water. There is a 2 here and a 2 here. We can take care of that after the fact. The first thing we want to do is just go ahead and get them, write the correct formula. So we've got this and this. This is copper 2+. I know that because chlorine is a 1- and there's 2 of them. So this has to be Cu2+. And then carbonate is always CO3 2-. So flip flop, it'll be a 1-to-1. So plus CuCO3. Now to balance this thing, I'm going to put a 2 here. Now it's balanced. So this is really the one in question is this a, does this form a precipitate? And in fact, it does. So if you were to look this up on the solubility charts, we would find that that thing does like to form a solid, okay? So looking at this, I would say it's a precipitate reaction. Again, I'm not going to expect you to have those solubility charts memorized, but you would need to be able to identify that this is in fact a precipitate reaction. You would need to be able to come up with the possible products, so on and so on. All right. Great, so we did that. There are possible products. We end up looking that thing up on the solubility charts, and it does in fact show that it's a solid. And then balance it. All right, so the next thing we need to talk about when writing a chemical equation is what's known as the molecular equation, the complete ionic equation, and then this thing called a net ionic equation. So in a molecular equation, which is what we've been writing thus far, all of your compounds are written in their molecular form, right? So when I write AgNO3 aqueous, I keep it clumped together. Even though I know it's dissociated in solution, I still write it together as an equation or a molecular formula. When I'm writing a complete ionic equation, sometimes I call this the complete pain in the butt equation because it takes some time to write it out. What you're going to do is anything that's aqueous, you're going to break it apart into its ions. So this thing here, and then also this thing here. We're going to break those up. So I'm going to write it as Ag plus aqueous plus NO3 minus aqueous, because if this is aqueous, it's really these things floating around in solution. I will do it for the sodium and the chlorine as well. Put a little arrow in to separate them out. I keep this as a solid or as a block. Okay, I don't break that apart because it's not aqueous. That is going to be true for anything that's a solid, a liquid, or a gas. All right, you're only breaking up the aqueous things. And then we break up our sodium and our nitrate over here. So now we've got a complete ionic equation showing us all of the ions in solution that we're starting with, and then any precipitate and remaining ions left over. Now, why is that important to write it like that? Because it can lead to what's known as a net ionic equation, which is just pretty much telling you what the important stuff is doing. So let's look at here. We've got this equation. This is the same thing from the previous page. Now, there are certain ions that aren't actually involved in the chemical equation themselves. They're sort of just acting as like a delivery system for the important stuff. So these will be called spectator ions. And how you identify a spectator ion is it will be the same on the starting side as it is on the ending side. So here, sodium and sodium. The only thing that the sodium did in this situation was to deliver the chlorine, right? Over here, the sodium is still by itself. So it's not really involved in the actual chemical reaction. Same thing with the nitrate. The nitrate stays intact. It stays just as a nitrate ion. It doesn't combine with anything. So again, its job was to deliver the silver to the reaction. So we can kind of cross these things out. because instead of it being sodium, it could have been like potassium that delivered the chlorine. It could have been rubidium that delivered the chlorine. It doesn't really matter as long as, the chlorine is really what's doing the important thing. So here, this silver and this chlorine, they meet at the party and they make magic happen, right? And they become a precipitate. That is the actual important component of the reaction. So we call that the net ionic equation. So we've got the molecular equation, we've got the complete ionic equation, and then the net equation, the net meaning just looking at the important stuff or what's going on overall. So we can see silver is brought in to see chlorine and they produce a precipitate. So I'm gonna have you all write, let's do it for that previous one. Let's do it for this, yeah. Let me clean it up a little bit though. So we've got CO3 aqueous plus copper produces 2NaCl aqueous CuCO3. So this is the molecular. I want you to write the complete ionic equation. And then I also want you to do the net ionic. Okay, so do complete equation and then the net ionic equation. Take note that you've got multipliers. So you've got 2, you've got a 2 here. So make sure you're taking that into account when you're counting up or adding how many ions you have on each side. So I'll give you all 5 minutes to work on that, breaking up all the things that are aqueous and then seeing what's really doing the important stuff. Again, if you have questions over the next 5 minutes or so, feel free to ask me. Otherwise, go ahead and chip away at that. Okay, so let's go ahead and break it up. So we've got sodium and carbonate. So I'm going to break those up into the ions. Now the polyatomic ions you keep as polyatomics. We don't break that up into carbon and oxygen. So I have sodium and, oh, no, I don't like that. Don't want to use that. Okay, sodium, which is Na, and it's got a plus charge. And this is aqueous. Now I need to take into account that there are two of them. So I'm going to put a 2 in the front of it. I don't want to put the 2 down here because it's not a diatomic. So when it breaks up, it won't be like 2 sodiums bonded together. I've got one of these carbonates. So CO3, 2 minus charge, and you do include the charge when you're doing the complete ionic. What do I have? A copper, Cu with a 2 plus charge. This is aqueous. And then I've got 2 chlorines, 2Cl minus aqueous. Okay, and this is going to yield, this thing gets broken up. So I've got 2 sodiums, 2 Na pluses, aqueous, plus 2 Cl minus aqueuses, plus this thing I keep together as a whole, CuCO3 solid. Why do I keep that as a whole? Because it's a solid, it's not aqueous, it doesn't break apart. So this is the complete ionic equation. Now, if I want to make the net ionic equation, I need to go ahead and see which ones are spectators. So sodium and sodium are the same. So I'm going to put a slash through those. Chlorine and chlorine are the same, slash through those. Those were just delivering the important stuff. So let's see. If I write just the important things, and I'm gonna put my metal first. I like writing the metal first. So Cu2 plus aqueous plus CO3 2 minus aqueous is going to produce CuCO3 solid. That is the net ionic, that's the important part. So what questions do you all have, if any, on that? Just want to make sure everybody's good with that. Okay, keep moving forward. So now we're going to start to look at some of the other types of reactions that are out there. So acid-base reactions are a type of reaction that you're going to want to identify. It's when you have an acid, and for now you're going to classify something as an acid as if it has that H in the front, combines with a base, and you're going to classify a base as of right now as having OH in it. Okay, so it's going to have this hydroxide ion. There are other things that can behave as bases, but we're not going to get into that just yet. So for right now, we've got an H sitting in the front, we've got an OH sitting in the back. Now what happens is when I take an acid and I combine it with a base, I'm going to produce water and a salt. So those are always going to be your two products in this sort of simplified acid-base reaction. So the H here combines with the OH here, and that's what's giving you the water. And then whatever's left over, the Na and the Cl in this case, those two are going to form a salt. And when I say salt, I just mean something that's a metal with a non-metal. The salt is usually aqueous. The water is going to be in liquid form. If I was to do the complete ionic equation, which I'm not going to write it all out, but if I was to do that and then look at the net ionic equation, anytime you have an acid and base coming together in what's called a neutralization reaction, we're neutralizing the acid and the base. This is going to be its net ionic equation. It's this H plus, which is coming from the acid, combining with the OH minus, which is coming from the base, and it gives us H2O liquid. Here are some common acids. You can see that they all have that H sitting in the front. Here are some common bases. They have that OH sitting on the back end. Again, anytime we take one of these and combine it with one of these, we're going to get water and a salt. Another type of reaction that we can get, which a lot of times is a type of neutralization reaction, is a gas evolution reaction. So we'll have, excuse me, we'll have two things that are aqueous, they'll come together and one of the products will actually be a gas. So looking here, and again, a lot of times these are neutralization. So I have an acid combining with what's behaving as a base. I get water, I get salt over here, and then I get this gas released. I wouldn't expect you to know how to take these two things and tell me what the products are, but I would want you to be able to identify a gas evolution reaction. And the best way to do that is just to look and see if a gas is popping out on the product side. Okay. Oxidation reduction reactions. So for oxidation reduction reactions, I want you really just to know the definitions of these. I'm not going to have you identify oxidation reduction reactions or do any sort of oxidation reduction. So think of this as just sort of a definition understanding. So sometimes these are called redox reactions because we have reduction and oxidation happening in the same reaction. Rusting of any sort of metal, bleaching hair, the batteries, electricity, that sort of stuff is all going to be oxidation reduction. And a lot of times oxidation and reduction happens when something combines with oxygen, hence that oxidation. So you do need to know this, in oxidation and reduction reactions, one thing will gain electrons and the other thing will lose electrons. So there's a couple different mnemonics to memorize that. One is oil rig. The other one is Leo the lion goes grr, okay? Oil rig, oxidation is loss. So whatever is losing the electrons is going through an oxidation. Whatever is gaining electrons is being reduced. And again, if one thing is losing electrons, the other thing has to be gaining it. So we will have oxidation and reduction happening in the same reaction. So again, notice oxidation and reduction must occur together. One substance loses, another substance has to gain. And that's really the extent of oxidation reduction for right now. Some of the things that you'd see that identify that it's an oxidation reduction, a substance mixing with oxygen, a metal combining with a non-metal, or any situation where you have a transfer of electrons. Oh, excuse me. My coffee is doing the opposite thing than I need it to do. It's making me sleepy. Okay, so combustion reactions are a type of oxidation reduction reaction. You will need to be able to identify a combustion reaction and you will need to be able to tell me what the products are. And it's pretty simple. You'll have some sort of compound containing carbon and hydrogen. Sometimes it's carbon, hydrogen, and oxygen. But what's going to happen is this hydrocarbon is going to combine with oxygen and you're going to produce heat, CO2, and H2O. So I'll give you one of these. So you want to be able to identify combustion reactions. CH3, no, definitely not CH3, CH4, methane combines with oxygen. If I was to give you this and say, hey, this is a combustion reaction, write the products. The products will always be CO2 and H2O. Okay, if instead of methane, we did C2H6 plus O2, then the products will still end up being CO2 and H2O. Those are the products in order for it to be combustion. So as far as, balancing this is concerned, balance carbons and then hydrogens and then do the oxygens at the end. So here I've got one carbon. Here I've got 4 hydrogens. Here I've got 2 hydrogens. So I'll throw a 2 there. That gives me 4 oxygens on that side. So I'll put a 2 there. Okay, again, balance carbons first. So I've got carbon, hydrogen, oxygen, 2, 6, 2, 1, 2, 3. Okay, carbon first, so I'll put a 2 here. That changes this to 2. It changes this to 4, 5. All right, then if I've got 3 hydrogens over here, I could put a 3 here. That changes this to 6. It changes this to 3. 3. Oh, something's not right here. Carbon, carbon, H. One, 2, 3. Yeah, no, that's right. Okay, let's see. What do we need to do here? So we have 3, 4, 7. All right. So I'm going to need to 7 over 2 this. So this would be 2. This will change to 7. This will change to 4. And this will change to 6. And that should balance it out. Okay. But really important thing I want you to be able to do is just identify that this is combustion, right? So some sort of hydrocarbon combining with oxygen to produce CO2 and H2O. Let's see, where were we? So here's a way to sort of understand all those reactions. So I've got a chemical reaction. I can identify it as a precipitate reaction. Again, precipitate reaction means that it's going to form a solid. Acid-base reactions or neutralization, we have an acid combining with a base to produce water and a salt. So if we want here to give us a little bit more detail, this is going to have water and salt as our product. Gas evolution reaction means that you're going to have a gas as one of your products. Okay, here, precipitate, you're going to have solid as a product. Oxidation reduction reactions, that's oil rig. All right, so oxidation is loss, reduction is gain. Again, I'm not going to really have you identify those outside of combustion reaction. So combustion reaction, we've got some sort of HY plus oxygen produces always CO2 and H2O. It's going to be our sort of skeletal structure for a combustion reaction. Now there's another way that we can classify our chemical reactions based off of what the atoms themselves are doing. So you can layer this on top of those other classifications. So something could be an oxidation reduction reaction and also be a decomposition reaction, okay? So the way that we're gonna classify based off of what the atoms do is synthesis or combination. So this is like a, A meets B and they become AB, so they start dating. Decomposition is our breakup situation. So we have a couple AB and for whatever reason, they're gonna break apart into a separate A and a separate B. Single displacement, this is where you have a solo person here, and then we've got a couple here and A bumps B out, or we switch A with B and then B is sort of left on its own. And then this double displacement, AB plus CD gives me AD plus CB, or this is that sort of swinger situation, right? Where we've got a couple and a couple and they flip-flop partners. So all of our precipitate reactions that we've seen have been in this structure. So you could say it's a precipitate reaction and it's a double displacement reaction. So let's look at a couple examples of each of these. One synthesis reaction that we have is the synthesis of sodium chloride or table salt. So you take sodium, you combine it with chlorine gas and you get sodium chloride. They were separate entities and now they've combined into a solid. Decomposition, so this is the decomposition of water. You can do this, it's actually pretty simple. You can do it with a battery. You take liquid water, you break it apart into hydrogen gas and oxygen gas. All right, so it's in its components. Single displacement, sometimes you can think of this as like the home wrecker, right? So you've got zinc, it moves into a situation where there's in this case, copper chloride, the zinc is going to switch places with the copper, okay, or it boots the copper out of solution. What will end up happening is you actually get the zinc moving into solution, and the copper that was in solution will actually deposit itself onto the zinc stick. So they flip-flop spaces. And then we've got our double displacement. This is where we have two compounds and they flip-flop their partners, okay? This is precipitate reactions, acid-base reactions, gas evolution reactions. All of those usually tend to be these double displacement. All right, so we can classify as synthesis, decomposition, single, and double displacement. So I want to pull up that balancing sheet that we had earlier and just go through and classify a couple of them. Okay, so if we're looking at these equations here, this first equation, I've got nitrogen combining with hydrogen to produce NH3 or ammonia. I'm not going to have us balance. We already balanced these, but what I want us to do is just classify what they are based off of what the atoms are doing. So in this case, I've got two individual things that are coming together to form a compound. So this would be synthesis or combination. Over here, I've got a compound that then breaks apart into, not into its individual elements. We've got one element here and then we've got a salt here, but we could still classify this as decomposition. It's breaking down. Here we've got sodium chloride and fluorine. And what we notice is that the chlorine and the fluorine end up switching places. So this would be a single displacement. One of them, or single replacement. One of them is getting swapped out by another. Here we've got hydrogen gas and oxygen gas coming together to produce water. This would be synthesis or combination. This right here, I've got lead with hydroxide and then, so this is an acid-base neutralization reaction. So here's our base, it's got that OH. Here's our acid. And we produce water and a salt. This would be a double displacement reaction as well as an acid-base neutralization. Here's another double displacement. So the metal here is going to combine with the non-metal here and vice versa. So they flip-flop partners. Each one of these, 7, 8, 9, all of those are combustion reactions, right? We've got some sort of hydrocarbon, carbon and hydrogen, combining with oxygen to produce our CO2 and our H2O. So that is the end of chapter 7. Are there any questions about what we went over in chapter 7 or anything that you guys want me to do some more examples of? So now's the time to ask because we have some time here. We're not going to meet on Wednesday, but that's it for chapter 7. So let me know if there's some more practice y'all want to do. If you're like, no, I'm good, I got this, then you're free to go for today. I'm not going to force y'all to stay around. Have fun tomorrow. Good luck. If you haven't voted, go vote. Would you do some more conversions with Avogadro's number? Yeah, we could definitely go back to chapter 6 stuff. Totally. So then face-to-face. Yeah. Okay, great. Yeah, we can do some of that. Face-to-face, I won't really see you guys until next Monday. Okay. So if you're out, goodbye. Otherwise, we're going to do some stuff with Avogadro's number. Okay, Gabriella and Leanna, let's do, I'm going to give you that you have 18.17 grams of silver. I want you to find how many silver atoms that is. Okay, so I'm gonna give you about 2 minutes or so to set that up. Hopefully you have that flow chart written down somewhere from the last lecture, and then we'll go over it. No, I'll give you longer than 2 minutes. I'll give you about 4 minutes. Okay, so for this guy here, I'll write the flow chart. I'll do at least do part of it. So I've got grams of the element. And I want to go over to number of atoms. So first thing I need to do is stop off in moles of the element. The mole is our sort of crossroad for the element, for our composition quantities. Come on. Sorry, my pen is not getting registered on my Zoom pad. What's going on here? All right, and then from here, this now we can do atoms, number of atoms. Now, how do I transition from each of these? Well, to get from grams into moles or moles into grams, this is molar mass, molar mass. And because we're dealing with silver, it's specifically going to be the molar mass of silver. Okay. Now, to get from moles into individual particles or particles into moles, this is where we use Avogadro's number as our conversion. So start with our given information, which is 18.17. So we have 18.17 grams of silver. Now I need to hop into moles. So 1 mole of silver is equivalent to the mass on the periodic chart. Where is my formula sheet? We've got, where are you, silver? 107.87. Hold on, sorry, I don't know why my pen keeps shorting out on me. So frustrating, there we go. 107.87 grams of silver. And that means that our grams will cancel. Remember, the number always goes with the gram, the 1 will go with the mole. Now from here, moles of element into number of atoms. This was, I think, specifically what you had asked about, Avogadro's number. So mole is here, so I need to put the mole down here. 1 mole of silver, or really 1 mole of anything, is equal to 6.022 times 10 to the 23rd individual components. So if we were talking about a molecule, it would be molecules. In this case, we're talking about silver. So this is silver atoms. And that will leave my mole value gone. So when plugging this into your calculator, 18.17, we're going to multiply it by Avogadro's number, 6.0, 18.17 times 6.022 to the 10 to the 23rd. And then we got to divide it by that 107, the molar mass, 0.87. I get a value of 1.01 times 10 to the 23rd silver atoms. Okay. Questions on where those numbers came from, especially Liana or Gabriella? Questions on any of that, or did that get to what you wanted? Do you want to do some more? Is there a certain part of that you want to go over? Let me know. Let's see. Makes sense now. Okay, let's do, why not, while we're here, why don't we go ahead and do one going in the other direction? All right, so I'm going to ask you how much a certain amount of atoms weigh. Because you can never have too much practice with this stuff, I don't think. So given that we have 1.06 times 10 to the 24th PbOH2 molecules. So you've got a lot of molecules. I want you to find the mass in grams. So I'll give you all, I'll give you about 6 minutes for this one because you got to calculate the molar mass. Okay, so oops, sorry about that. For this one, we're going in the opposite direction, and we have a molecule instead of a single element. So we do have to calculate the molar mass of this thing. So I'm going to do a flow chart for this. So in this case, we've got molecules, specifically of PbOH2. And I need to go to moles of PbOH2. And then from there, I can go into grams of PbOH2. So we start with the molecules. We get 1.06 times 10 to the 24 PbOH2 molecules. In order to get that into moles, 1 mole of PbOH2 is equivalent to 6.022 times 10 to the 23rd PbOH2 molecules. So Avogadro's number goes in here, Avo's number. This will be the molar mass of the compound. So in order to go from now moles into 1 mole of the PbOH2, we need the molar mass of it. So uh, 241. 241.21 grams of PbOH2. Something in the comments. Let me see what. Oh, thank you. So when plugging this into your calculator, it's important to use parentheses and or the EE button for your exponent, because we're dividing by the Avogadro's number. So we're going to take our 1.06 to the, what do we say, 24th. We want to divide it by 6.022 EE 23rd to keep that thing intact. Make that look more like a 6. So either you parenthesis out that number or you EE it. And then we're going to multiply it by our mass, 241.21. All right. Come on, pen. That's where I'm trying to write right now, everybody. Cursor's not moving. Come on. Okay, cancels, and we'll be left with units of grams. And I ended up with, we have 3 sig figs, so let's go 3 sig figs, 425 grams of the lead 2 hydroxide. Questions on that? Where all that stuff came from? Any other stuff you guys want to go over? Hi, Harley, that you're welcome. Let's see, Gabrielle, could you also go do a refresher on how to find the mass and percentage of an element in a compound or formula? So mass percent stuff. Yeah, let's do that. All right, Leanna, glad you're good with that. So let's look at, well, let's do lead, that lead 2 hydroxide, PbOH2. So I want to know what the mass percent of oxygen is in this thing. All right, so in order to do that, we're going to take the mass of oxygen, but we need to multiply it by 2. Why? Because there are, in fact, 2 oxygens within that compound. And then we're going to divide it by the mass of the compound, or the mass of the whole thing, the PbOH2. Okay, so this works itself out to 16 times, oh, and I'm sorry, let's multiply this whole thing by 100 because it's a percent. So 16 times 2 divided by that, I just had it written down somewhere. 241. Come on, okay. 241.21. Okay, and we multiply this thing by 100. And we end up with 13% roughly. 13% of it is oxygen. Go ahead and find the mass percent for hydrogen in the same compound. Okay, so for this one, we're going to take the mass of hydrogen times 2, because there's 2 of them, all over that mass of the lead hydroxide, lead 2 hydroxide, so 241.21, and this is ends up being 2.02. Okay. We multiply it by 100. And so it's a pretty small percentage. So in this case, it's only 0.84%, less than 1% of this is hydrogen. It's because hydrogen is such a light atom compared to lead. Lead is a real heavy atom. Yeah. How's that work out for you, Gabriella? Perfect. Okay. Anything else before we head out? Ooh. Oh, why am I so sleepy this morning? I think I would be less sleepy with the time change. Awesome. Lyric, yeah, we can chat in just a sec. All right, well, we'll call it for lecture today. So good luck this week. Message me if you have anything you want to talk to personal about. Lyric, I will bump into you in just a sec, all right? So bye, beautiful people, have fun. Lyric, what's up?
Sorry, I look crazy, but
Oh, no, don't worry about it.
but I took my hair out. I have hairdos like new hairdos like every other month, so I took my hair out and I just haven't did
Took it out.
anything to
Yeah, well,
it.
you look beautiful. So.
Thank you. My master in chemistry is still not working. I emailed
Okay.
them. I haven't got a response back. I don't have any other electronic or like any other computer to work on. And I know I could go to AB Tech, but I don't have a ride either. I don't have a car,
Okay.
and my mom works, so I don't want like my grade to go down. So I don't know what.
Don't
else to
stress
do.
about it. Yeah, I can give you an extension on it. We'll just
Okay.
keep trying and see if we can figure it out. Don't stress about it, okay?
Okay. Okay. Thank you so much.
Yeah, we'll figure it out, okay?
Okay.
Okay, cool.
All right.
Lyric.
Have a nice day.
You too. Bye.